All right. So we've already talked about matter, and now we're going to connect measuring of that matter to that, because that's really what becomes important during chemistry. You know, in math, you deal with numbers, but in sciences, you deal with important numbers because they represent something, a measurement you've taken, and they have units with them. So we're going to start off with a little background about scientific method. I know that y'all have done that before, so it's just going to be short. There will not be a quiz over scientific method. You'll probably see a couple questions on the test when we get to that. I will not ask you to list the steps or anything like that. And then we'll move on to sig figs, and the quiz for sig figs will not be until next Wednesday. That way, if you work on some practice throughout the weekend and you have some questions, you'll have a chance to get those answered on Tuesday before the quiz. All right, so the scientific method is a logical approach to solving problems by observing and collecting data, and that's usually done during experimentation, and then formulating and testing hypotheses, and then if the hypothesis is supported, you can go to the next step, which would be formulating theories. So the scientific method sets scientific standards. And what I mean by that is that scientists like to share information, especially if somebody else's information will be helpful to them, because to carry out all these experiments is obviously very expensive. And if all scientists know that they're following the same method, then they know that the information or the data they're getting from another scientist comes from a good source and under the same conditions. So it's easier to rely on that. Observation involves making a measurement when something is being observed and collecting data. Data may be qualitative. So that would be something like saying sulfur is yellow or sulfur stinks. And quantitative, quantitative, which is numerical data. Yeah, somewhere I did something wrong, right? Did I leave out a T here? Feel like somewhere. I'll spell it one more time in case. quantitativ is what I left out. So that's numerical. That's mainly what we'll be doing in chemistry. So that's like taking a measurement and saying something is 10 grams. Experiments involve carrying out a procedure under controlled conditions. Does anybody remember what controlled conditions mean? Maybe from biology. If something's in control, what does it mean? You keep it the same, or yeah, you control it. You keep it the same so you can compare to it. So like if I was trying to test whether fertilizer would make tomato plants grow taller, if I didn't have a control to compare it to, how would I know they're growing taller or not? I would need a plant that wasn't getting the fertilizer. And once again, that type of experimentation just is good standards, and then it's easier for information to be traded between scientists. Formulating hypotheses starts with generalizations, which are statements that apply to a range of data. And then the next blank is generalization 2. I'm going to put ditto marks, although I'm kind of finding out y'all don't really use ditto marks, like to show that something. It's just a way, like if you have the word right above it, you can use ditto marks and it shows it repeats. So a little shortcut. Generalizations are used to form a hypothesis. Which is a testable statement. And it often uses if then statements. So like, if I give the tomato plants fertilizer, then will they grow larger? And then I can do experiments and gather data and numerical data, so quantitative data, and check that all out. Testing a hypothesis involves experimentation, and it's used to either support or reject a hypothesis. And in real life, more hypotheses are rejected than they are supported for scientists that are doing this for a living. My youngest daughter just started her PhD, but for 2 years, she worked on the same experiments trying to prove something for a doctor that she was working for, and nothing was ever proven. And that was after 2 years, and I'm sure it was very expensive. So I that could maybe be a frustrating job if you're trying to prove something. So then they had to regroup and come up with another idea. And so now she's working toward that. But a lot of times things are not actually supported. If your hypothesis is supported, then you can move to theorizing. So that's coming up with the theory, and a lot of time it is represented by a model, which is an explanation of how phenomena, PHENOMENA, occur, and how data of events is related. So any kind of experimentation that happens, data has to be gathered, and then that has to be evaluated to see whether it's supported or not. So that's just a little brief thing about scientific method. And of course, the part that we really are interested in chemistry is kind of the gathering data part and then using that data part in other calculations. So for that, we need to know our different units of measurements. So a quantity is something that has size, magnitude, or amount. So in math classes, you use quantities, but in science classes, you use measurements, and they are not the same thing. In math class, you may use 100 to do some kind of calculation, but in a science class, 100 doesn't mean anything. Is it 100 meters, 100 grams, 100 seconds? So you have to have that unit attached to it so you'll know what kind of measurement was taken. The SI measurement, or the SI unit, is another name for the metric system, and that's called System International. Is what it stands for. And it was adopted in 1960, and it has 7 base units. And although it's not used, maybe, well, the United States may be the main place where we don't use the metric system. If you go overseas and you start seeing like kilometers per seconds, maybe, or hours, I'm not for sure what their time would be. But our scientists here do use that. So in the scientific world, everybody would use that same system. And once again, if they didn't, it would be hard to trade information and trade data. So there's 7 standards, and a standard has a constant value, and then everything else is built around that. So the 7 standards for the metric system, we're going to look at those. We won't use all of them in chemistry. So the first one is length. L would be the symbol. The standard is meter. And big M. So what I mean by the standard is like when they were deciding about this system, somebody decided what the meter was, how long that was, and then they could tack on the prefixes. So if it was a kilometer, you add 1,000 meters together, but something had to be decided on first. And in this case, the standard was the meter. Mass, and we do use mass a lot. Little m, kilogram is the standard, and its abbreviation is kg. Gram is the base because that's the one without any prefixes on it, but kilogram was the standard. So once again, kilogram was decided. Then you divide that by 1,000 and that gets you down to the gram and so forth and so on, and you move from there. And the good thing about the metric system is you're just moving decimals. You're not like really multiplying the number. So like with the English system, there's 12 inches in a foot. So if I'm converting from feet to inches, not only do I have to worry about moving the decimal, but then the whole number's changing. Whereas the metric system, it's just the decimal moving. Time, little t. Second, S represents that. Temperature, which we use a lot in a unit called gas unit. Big T, and we use Kelvin, even though that's not used enough a lot in the United States. On the Kelvin scale, there are not negative numbers, so that's why it's nice to work with. Big K. Amount, we also use that a lot. Little n, which stands for moles. MOL is the abbreviation. Electric current, I use more in physics. Current, the unit would be ampere, or we tend to just say amp. And a big A, and then I'm going to have you add on one because it got cut off. Luminous. It reminds me of Beauty and the Beast. Luminaire. Luminous intensity. So like luminaire was a candle and burned bright, that's what it's measuring. Luminous intensity is measuring how bright a light is. IV is a symbol, looks like Roman numeral. Candela is the unit, and then CD would be the abbreviation. Once again, more something that you might come across in physics, not so much in chemistry. Ma'am? IV, like a Roman numeral, or probably it's a small L and V, but it looks like a Roman numeral to me. All right, we use a lot of derived units in chemistry. And derived units are units that have more than one unit. It's a combination of base units. So for instance, if area is equal to length times width, and I know the length is 10 centimeters and the width is 10 centimeters. So 10 times 10 would give me 100. That takes care of the number, but the centimeters were also multiplied by the centimeters. So that's where you would get the centimeters squared. So you get derived units from either multiplying or dividing with units. You would not get derived units from adding because those just are carried through. They're not multiplied or divided. So area, that's where I get my square meter, meter squared. Volume, because it's length times width times height, I end up with cubic meter. So it would be my meter raised up to the 3. Molar mass, which we use a whole lot in chemistry. Little m, the derived units is grams per mole, or G per MOL. MOL is the abbreviation for mole, not little m, because that represents something else. All right, what we're going to spend the majority of our time on is significant figures. They are very important because we use them throughout the year. And start off with, you just get better with them by doing the practice. And we'll continue on them tomorrow. And like I said, we won't do a quiz on that until whenever we come back on Wednesday. But once you've learned sig figs, which is today, then it affects all calculations that we do. So significant figures are used to indicate the precision of a measured number. Once again, you don't have measured numbers at math, so you don't have to worry about sig figs. Or to express the precision of a calculation with measured numbers. So any measurement, the digit farthest to the right is considered to be an estimate. So if I have this ruler, it doesn't have very many demarcations. It just has 1, 2, 3, kind of like a beaker. So if I was trying to measure this spot right there, the only thing I know for sure is my 2. That 0.0 after it is my estimate. And that's true for any measurement. A measurement may have 6 places. The last one is always an estimate. So when we're working with sig figs, let's say that I have a measurement and it's 10 centimeters. So that means I only really know one thing for sure, that it's in the 10 range. It's not a very precise number. Now, if I use that 10 centimeters and I do some kind of calculation, does it make sense that I get an answer that's 1.4576823 centimeters? Does that make any sense? Nope. And that's what sig figs are all about. On this number, I'm saying I know all of these for sure, and I just had to estimate that one. And there's no way you would know that much from something that originally when you took the measurement, it was not very precise. So that means that now when you do calculations, you're going to have to see what you got in your calculator, and you're going to have to adjust it to the right number of sig figs, because the calculator doesn't do that. So that's what sig figs are about. The whole thing about sig figs is that you cannot make a calculation that is more precise than the digits given to you in the measurement. That's the whole basis of sig figs. So we're going to talk about the rules, and then we'll talk about how they're put to use in some of the calculations. So first rule for significant figures. And with significant figures, we're really looking at zeros. When you get down to it, if there's a 0 in a number, you're trying to decide, is it significant or not? So the first one is the easiest. If I have all non-zero numbers or digits, it's all significant. So if I have 125, there's no 0, so that's 3 sig figs. If y'all will change this 5 to a 4 right there, I cut and paste that from somewhere else. And then this one too. I thought there was another one, and I didn't catch those mistakes. So if I have 325,111, no zeros. That's the easy one. That's going to be 6 sig figs. The next one is kind of the second easiest rule. All zeros between non-zero digits are considered significant. Because remember, if they're between non-zero numbers, they're not the estimate. There's still something following them. I call them sandwich zeros. So here I have 101, 3 significant figures. I could have 1, I could have 8. I could have 8 zeros in there. The fact that those zeros are sandwiched between the ones, they're significant. This would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 significant figures. Then the rules get a little bit harder. Zeros following a non-zero digit and a decimal are significant. So if I look at this number, I have 3 zeros I have to worry about. These 2 zeros, I'm going to talk about those first. Those 2 zeros follow a decimal and follow a non-zero number, so they are significant. This 0 does not. That first 0 is not significant. It's considered a placeholder. It does not follow a decimal and it does not follow a non-zero number. Zeros following only a decimal are not considered significant. So that would be something like this. It's usually with a very small number. These are my zeros. None of those zeros follow a decimal and a non-zero number. So all of those are considered placeholders and you only have one significant figure. The next rule says zeros following non-zero digit only are not significant. So that would be some larger number where those zeros are behind a non-zero number, but they're not behind a decimal. That means that is only one significant figure. That would only be still one significant figure because those zeros are not behind a decimal. As I mentioned earlier, the last digit is always an estimate. And that means trailing zeros only count if there is a decimal. So these are trailing zeros, no decimal, it's just one sig fig. But once I put these zeros with the decimal, they become significant, and that becomes 4 sig figs. If I have 10,000 without a decimal, that is only 1 sig fig. That means the only thing I really knew was that 1. It's tired. It's tired. We're tired. We're all tired of hearing about sig fig. But if I have 10,000 and I put a decimal there, those now become 5 significant figures. It's kind of like that picture he did on the video where you didn't know how many people, like you could say I had about 10,000, but then if you actually did a measurement and maybe I mathed something out and it said it was 10,000 on the scale, then that's going to be a more precise number. That's the difference that the decimal makes. All righty, so those are the rules that you're going to be following and putting into play as we move through these. We're going to start off with just saying how many there are, but in reality, throughout the year, it's how you use them in a calculation. That's what really becomes important. All right, so I'm going to start with my first one. I have these leading zeros. Oops. Are those significant? No. So that's all my significant numbers right there. That's 5. Those are just placeholders. What about my 2.60? How many sig figs? 3. Perfect. That 0 is behind a decimal and behind a non-zero number. Nice, easy 6. 1. 670 without a decimal. 2. Perfect. 542,000. 6 because of the decimal. That decimal right there. Uh-oh. There's pigtails. Oh, Yes, and also. All right. So that's 6 because of that decimal. Without that decimal, it would have only been 3. And then the last one, no zeros. That makes it nice and easy. So that would be 6. Perfect. All right. Like I said, you got to kind of put it into practice a little bit. So another thing that's a pain about significant figures is that when you're doing calculations, there's one set of rules for addition and subtraction and another set of rules for multiplication and division. Sorry, I didn't make the rules. And when you go to college, they will not teach you this again. They'll expect that you know it and that you can put it into play right away in your science classroom, especially in your labs. So for addition and subtraction, the answer should be rounded off. So as to contain the same number of decimal places as the number with the least number of decimal places. So what that means, because it sounds like a riddle, is in other words, an answer can only be as accurate as the number with the least accuracy. So for addition and subtraction, you're looking at places behind the decimal. That's what you're interested in. This has 2 places behind the decimal. This one has 3, and that one only has 1. You always go to the with the least. So my calculator may kick this out, but I have to adjust it to get it correct and to get credit. And because of this one, our answer can only have 1 place behind the decimal. So that's where my 6 is. But because there's a 7, it would have to be recorded as 48.7. So if I put these numbers in my calculator, I would get 11.295. Could I leave it like that? No. How many places behind the decimal should it be?
1.
Just 1. So I should have 11.3. This one only has 1 place behind the decimal. 350 and 200, I get 150. Is that good? Yes, that was good because the 200 had no places behind the decimal. So I want my answer to have no places behind the decimal. So that's addition and subtraction. Now make yourself a line because now you got to get in your mind when I go to multiplication and division, the rules change and I go back to counting significant figures. And it makes it a pain. And we do much more multiplication and division throughout the year. So with multiplication and division, the answer should be rounded off to contain the same number as digits as found in the least accurate or least precise value. So in other words, if I look at these, this one has 4 sig figs. This one only has 3. And like I said, you always go with the least. So my calculator may give me that. But now that we know we're dealing with measurements and sig figs, I would have to adjust it to 18.1. The 0 is my third sig figs, and there's a 6 behind it. That's why it became a 0.1. All right, if I had 23.4 multiplied by 14, I would get in my calculator 327.6. Can I leave it like that? No. What do we think we would round it to? How many sig figs can we have in our answer? 2, right? So we know the 3 is good. Since here's my 2, since there's a 7 behind it, what am I going to do? If I put 20, this is a hard one. This is a hard one. No, you're fine. If I put 28, because that seems to make sense, don't write it down. That leaves me with 3, right? So let's not do that. So we say 3, 3, right? Because there's my second sig fig. I'm around it to 3. Do you think I can just leave it as 33? What do you think I need to put? A 0 without a decimal. That means it's not significant. It's just a placeholder. I can't go from something that's in the hundreds down to something that's just in the tens, but those are tricky. Those are the ones that are kind of harder. Oops, I don't know what it is. And then my last one, sorry, I didn't mean to erase all that. If I put this one in the calculator, I would get 2.5. Can I leave it as 2.5? Yes, no? Yes, right, because this one has 2 sig figs. All right, dealing with scientific notation and never can remember. Scientific notation is sig figs. Like I said, I'm not going to go over how to write or read scientific notation because y'all have already done that. And I have a little video for you to refresh your memory. But if you're looking at a number that's already written in scientific notation, your sig figs come from the coefficient, not from the base or the exponent. So like this one would have 3 sig figs. If I looked at my next one, once again, I'm not interested in the coefficient, so that would have 4 sig figs. If you're moving between the two, you have to maintain the same number of sig figs it originally had. After you said sig figs 1,000 times, it gets hard. So in other words, if this originally had 5 sig figs, right? When I put it into scientific notation, it still has to have 5 sig figs. So I'm going to move my decimal 1, 2, 3. So I get 3 point, oh, we don't leave me yet, times 10 to the positive 3 or negative 3. Y'all know. I move my decimal to the right. Am I going to get a positive 3 up here or a negative 3? Anybody vote for negative 3? Remember, if it's so, y'all be sure to watch your video because y'all can need it tomorrow. Remember, if it's a small number less than 1, you're going to have a negative exponent. If it's a large number, then you'll have a positive exponent. Okay, I promise you, y'all have learned that. You just need to have your memory refreshed a little bit. I know it. When you go to college, when you get to be a senior, they're going to think you remember stuff from when you were a freshman. Isn't that crazy? Same thing here. This had 4 sig figs. So if I write it out, it's at least have 4 sig figs. Sorry, y'all. 0.000980. I'm maintaining my sig figs. I don't think I can say sig figs for any more times until I get to 8th period. All right, so please do some practice. We're still going to be working on it tomorrow on a little web quest. That's why you're going to need your Chromebooks and you're going to need to know how to do some scientific notation. So please watch that. And I was really happy with the grades overall. I just want to say, I feel like of my classes, like this class had the highest overall grades of any of my classes in a long time.